So as we look at rates of change and we look at how, so previously we did between rates of change between 2 points, rates of change as an average over a longer period of time. And now what we're looking at is rates of change at an instantaneous point of time. So how would we measure the gradient between 2 points that are like almost right next to each other? So what you're going to be asked eventually to start doing is you're going to be asked to start finding the gradient of a curved line. So for example, there's a really disappointing looking parabola. And by that, I mean a really disappointing parabola. And what you're going to get asked is you're going to get asked to talk about the gradient of that curve at any particular point on the line. So for example, this is y equals x minus 5 x plus 3. All right, that's what it is. It is what it is. And it has a turning point. Where's the turning point, guys? It's halfway between minus 5 and plus 3. So that's going to be at 1. It's 4 units to the right, 4 units from there. So when x equals 1, we have a turning point. So that's at 1 minus 5 is minus 4. 1 plus 3 is 4, so that's y equals negative 16. I think that's right. Yep. What is the gradient between this point here at 116 and what about when x equals 2? So what's the distance? So when x equals 2, what's my gradient? Well, 2 minus 3, so 2 minus 5 is minus 3. And then 2 plus 3 is 5, so it's going to be minus 3 plus 5. That means y is equal to minus 15. So that means that if I were to work out the gradient between this point here and this point here, well, I can, just use m equals y2 minus y1 over x2 minus x1. And so that's going to be minus 15 minus 16 divided by 2 minus 1. And that means I'm going to have a gradient of 1 because negative 15 plus 16 is 1. 2 minus 1 is just 1 as well. So the gradient between here at 1 and 2 is 1. But the gradient between 2 and 3 is going to be different. So when x equals 3, 3 minus 5 is minus 2. So 3 minus 5 is minus 2. 3 plus 3 is 6. So it's going to be minus 2 times 6. That means y is going to be equal to negative 12. Now, so this is between these 2 points. But if I go over here, what about the gradient between these 2 points instead? What's the gradient between these 2 points here? So again, it's going to be y2 minus y1 divided by, so that's going to be, so this is going to be, this is x1, y1, x2, y2. So it's minus 12 minus 15 divided by 3 minus 2. And that means I'm going to have a gradient of 3. So what you notice is that the gradient keeps changing as I look along this line. Now, does anyone want to hazard a guess at what the gradient is if I go the other way? So this entire part of the graph, what's the gradient there going to be? What is it going to be, positive or negative? Yep, negative. And everything over this other side is going to be positive. And as we go further along, the graph is going to get more and more positive, and the graph is going to get more and more sharper. Whereas here, it's negative, 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 negative. What is it literally here? All right. And one of the things that we need to look at is looking at it as like, let's zoom right in on that spot. So let's compare, and we'll need our calculators to help us with this. What's the gradient between x equals 1, x equals 1.01? Well, actually, no, let's just go 1.1. So x is 1 and x equals 1.1. What is the gradient between those 2 points? And what we can do is, using function notation, we can express what we need to do. So remember that all coordinates can be expressed as, for example, a comma f of a. So all the coordinates are like that, and then so this is f of x. F of x equals this. F of a is when a equals x, or x equals a. Yeah. So just as someone's pointed out, this is negative, this is positive, but at the turning point, the gradient is actually going to be 0. What we're going to do is we're going to look at finding the gradient between these 2 points using this equation. And then what I'm going to do is I'm going to make that gap even smaller. So between x equals 1 and x equals 1.01 and 1.001. All right, and what you're going to see is that those values are going to converge towards a particular number. They are going to get smaller and smaller and smaller each and every time. So I'm going to get you guys to do some work very quickly, and you're going to help me fill out this table. So what is the gradient of 1 between f of 1 and f of 1.1? So to do that, again, using the equation over here, I need to find the gradient between these 2 points. So what is f of 1 going to be? Well, f of 1 is f of 1 is minus 16, so that's 1 minus 16. Can you guys help me find 1.1 and 1.01 and 1.001, please? Help me find those so that I can move on. I'll be back in a moment. And we're back. So we've got the points here, the sets of coordinates. As we're getting closer and closer to where our turning point is, as you can see, the number is getting closer and closer and closer and closer to 16. So what we can do is figure out, well, what is the gradient between these 2 points, so these two, and then these two. And what we're going to do is we're going to have, so it's going to be y2 minus y1. So let's do this one first. So this is A. So it's negative 15.99 minus 16 divided by 1.1 minus 1. So what does that come out as? Well, that's 0.01 positive because it's negative 15 plus 16. And that's 0.1 there. So what is that divided by that? So what is 0.01 divided by 0.1? All right, what is that? Use your calculators to help me find out. Yep, 0.1. Cool. Now let's do it with this. Let's do it with this next one. So that's negative 15.9999 minus 16. So that's A. This is B. Divided by 1.01 minus 1. Well, that's going to come out as 0.0001 divided by 0.01. What's that answer going to be? I'm guessing it's going to be 0.001. And then C for the coup de grace, negative 15.999999 minus 16 over 1.001 minus 1 is going to be equal to 1.00001 over 0.001, which is going to be 0.00001. So as the gap between the 2 points gets closer and closer and closer, you can start to say that it is for that particular point, it's just going to be 0. All right. What we are working towards is an algebraic way of working out the gradient at any point on a line. All right, at any point on a line. So I'm going to show you something that we're going to go into a little bit more next class, because I think it might help visualize what's going on a little bit better. All right. So if I have a formula, so I have f of x, and I have f of x is a particular spot. What if I now think about a particular equation that is, or a particular point on that line that is just a little bit either side, but I don't tell you what number that is. And I have, so for example, f of x equals x squared. Well, what is f of x plus 1? Well, that's x plus 1 squared. What is f of x plus 0.1? Well, that's going to be x plus 0.1 squared. What if, instead of thinking about actual numbers, I start thinking about it in terms of f of x plus h? H is just any number I want, but what we're going to do is we're actually going to say, well, what if h approaches 0? It's becoming 0. Now, if we think about doing function notation using our formulas, so if I'm working out, if I have f of x and I need to find out the gradient between a and b, so x is a and x is b, well then I could write it as f of b minus f of a divided by b minus a. So I can write that like that, and I can get my equation. Now I can do something similar with what's behind me. All right, I can do something similar with what's behind me with this infinite changing gaps. And so what I'm going to show you is f of x plus h minus f of x. All right. Some of you may know where I'm going with this. The gradient at any point on that line is going to be equal to this as the limit h approaches infinity, or infinitesimally small. H approaches 0. All right. So using this, let's actually just do it and try it out. All right. Let's figure out, well, what is x plus h squared? All right. So can I get someone to please tell me what that is fully expanded? Someone please tell me what that is fully expanded. X plus h all squared. All right. X squared plus h squared plus 2xh. All right, cool. All right, so it's x squared plus h squared plus 2xh. I'm with you so far? Cool. So, and by the way, this is x plus h minus x, and we can just cross those out and just leave h. So that's going to be x squared plus h squared plus 2xh minus x squared all over h. What happens to the x squared there and the minus x squared there? What happens? What's x squared minus x squared? What can I do with it? Cut. Yep. Gone. Just make sure you guys can... Yep. Oh, yep. So they go away and I'm left with h squared plus 2xh all divided by h, with my limit going on over there. What can I do now? What can I do with what I've got here? Cancel out. What can I cancel out, guys? factor out h and then cancel, so correct. So what I can do is I can go h bracket h plus 2x, all divided by h, and then the h cancels out. So that means that at any point on my line for my curve, the gradient at that point is going to be equal to 2x plus h, where h is the gap between the 2 points. But what if there is no gap? What if we do say that the limit is 0? That means that the gradient of any line on that point is just going to be 2x. I can now work out the gradient of any point along y equals x squared just by knowing that the gradient equation is this. And this is part of what we are going to do as part of the calculus unit. This is actually called first principles. And we are going to go over this for a few lessons. This is going to be a skill that you're going to need to demonstrate and show all the working out for. But the idea of doing instantaneous rate of change is building towards this concept that I've got here. All right, we are building towards this exact concept. So this should be what you need for 16E, where they are talking about instantaneous rates of change, where the gap between the 2 points might as well be 0. Because as you can see from up here before, these numbers, as the gap between the 2 points gets less and less and less and less and less and less and less, the gradient between those points is getting ever more smaller, ever more smaller, ever more smaller. And if I keep going, all that's going to happen is I'm going to get more and more zeros on there. And at some point, I might as well just accept that 0.000000000 for 6 weeks is just 0. It's so small that we can't possibly care about it. All right? It's so small that we can't even visualize it. We can't even measure it. Because, you know, you get enough zeros in there, you're talking about the sizes of atoms. All right? So it might as well just be 0. Gone. Chuck it out. All right?